Hi everyone, welcome to this quick recording. It's going to concern homework number 4. I've received several questions and I know that we briefly discussed it, but I promise for those who inquired that I will have more detailed video. So this whole homework, this whole session is going to be dedicated to that. So I will try to keep it short, okay? So let me share with you the screen. Let me first of all open the assignment. And let me share with you the assignment. So share. So hopefully you guys are looking at the screen in here that gives you the homework assignment. It's all related to basically Venus, namely units 39 and 40, 41. So hopefully you have access to the book by now. And these are the assignments. So basically the first assignment, it gives you the amount of carbon dioxide on the surface of the, or at least on the planet Venus. And it's 4.6 times 10 to the power 20 kilograms. And it tells you if you were to take extract all of the oxygen in that carbon dioxide and change it to water, H2O, basically how much water you're going to get. And it gives you some information about the atomic mass for hydrogen being 1, carbon being 12, oxygen being 16. So that's problem 1. And it also tells you to compare that number to the known value for the amount of water in the oceans on Earth, which is 1.4 times 10 to the power 21. We'll see that we'll get smaller number than that. Then the second problem is related to that. It gives you the density of water, which is known to be 1,000 kilograms, occupies a space of 1 cubic meter. So it tells you how high would that water, if in case you succeed to make basically water out of this carbon dioxide on the surface of Venus, how high it's going to stack, basically how high it's going to be on the surface of Venus if the surface of Venus basically is entirely covered by that water. So that's the second problem. The third problem in here, it gives you basically a way of finding how much an astronomical unit is. So you send a laser beam from the Earth to Venus. When they are at their closest approach, Venus will be at a distance which is 0.723 astronomical units from the sun, meaning that it's going to be about 0.277 away from us. So you send a laser beam, it hits the planet, it comes back, it takes 276 seconds to do that. Now we know how fast light travels. Based on that, we're going to find how much that distance is in kilometers. And we're going to find, therefore, how much is in astronomical units. Usually the standard value that is taken is 150 million kilometers, but we will see that it's going to be slightly less than that. Also, this problem in here gives you another thing in here, that the Earth and Venus, because Venus is inside, the path of Venus is inside that of the Earth when it goes around the sun. So they line up when we are in the inferior conjunction. Basically, what happened is the sun, then Venus, then Earth. Then 583.9 days later, they line up again. Okay, in other words, the sun will be on the other side from both of them, and they line up the three of them. Based on that, they are asking to show that the same side of Venus will always face the Earth. And that is related to the rotation of how fast actually Venus rotates around its own axis, which is about a fifth of that number. So we're going to discuss those numbers and how that makes sense. And finally, in here, it tells you if the Earth were to go in retrograde motion, like Venus does, instead of going forward, like what it's doing right now, while it's spinning forward. Let's say, for example, it's spinning backward while it's moving forward. In that case, what happened to the solar day? Obviously, it's going to be shorter than the sidereal day. So that's basically the problem. So I set them up. So let me go into another screen. Hopefully, you guys, by now, you have access to them and you're following me because I have them on that screen. So I'm going to be working on a different screen right now, which I'm going to share with you. Share the lower screen. Okay. So do I have a map? I think I do. There it goes. Anyway, so basically the first problem, it tells you that the amount of carbon dioxide on Venus right now. Can I write in here? It's not writing. We go to the draw mode. And is it? Let's select this pen. And it's touch draw. Okay, anyway. So carbon dioxide, the amount of mass that we have is 4.6 times 10 to the power 20 kilograms. We need them in grams. Okay, so we need to multiply this by 1,000. So when we multiply by 1,000 is adding 3 to this number. So this is how many grams of carbon dioxide right now we have on the surface of Venus. Now, we know carbon dioxide has one atom of carbon, which is 12 grams, and two atoms of oxygen, which is 16 each. So that's 2 times 16. And if I do the math, that adds up to 44 grams per mole. But I don't have 44 grams. I have this number, 4.6 times 10 to the power 23 grams. So I have this many moles, 4.6 times 10 to the power 23 grams divided by 44 grams. That's the number of moles. Obviously, the grams cancels, and it's going to give me a number. So I'm going to do the math. 4.6 times 10 to the power 23 divided by 44. Okay. That is how much moles you can have of carbon dioxide. That's how many moles of carbon dioxide you have. Each mole will provide 2 oxygen atoms because each mole has 2 oxygen atoms. That means this will give me 2 times this many, 4.6 times 10 to the power 23 over 44 atoms of oxygen. Because remember, 1 mole has 2 oxygen atoms versus 1 oxygen of carbon for carbon dioxide. So if I break this compound apart, I will end up with twice as many carbon dioxide twice as many oxygen as I would carbon. So in this case, that oxygen, each and every one of them will form a new mole with 2 hydrogen atoms to form basically water. So how much water I'm going to end up with? How many moles of water I'm going to end up with? It's that many. 2 times 4.6 times 10 to the power 23 divided by 44 moles of, I think moles, I don't know if moles has an E or not. I probably misspelled it, okay? It's not an E in here. Sorry about that. It's not a mole. Mole. Okay, no chemists are looking at it. Anyway, so this is how many moles of water you're going to end up with, because when you break the carbon dioxide, each carbon dioxide will give you 2 oxygen atoms, and each one of those 2 oxygen atoms can combine with 2 hydrogen atoms to form a new water molecule. Therefore, you have this many moles of water that you're going to form. Each water, though, has 2 hydrogen atoms, and each hydrogen atom weighs 1 gram per mole. And you have a 16 grams for the oxygen. So that's a total of 18 grams per mole, but you have this many moles. Therefore, the total mass of the water should be 18 grams per mole times 2 times 4.6 times 10 to the power 23 divided by 44. It's a big number. Ignore this number for right now. Ignore the power. I'm going to get a calculator and punch these things in a calculator. And I think I have GeoGebra, so let me open it to make sure it is open. So let me stop sharing and plug in those numbers in GeoGebra, and whatever it gives me, it gives me. So that's the answer. So I'm going to go to share. And what is GeoGebra? It's kind of a really honestly not good to have to record this by myself, because I don't know what the outcome is, honestly. So I'm going to share. Hopefully, you guys are looking at the calculator in here. So basically, this is the mass of the water that we're going to have. We have 18 grams per mole for water times the number of moles. And the number of moles is 2 because each mole of carbon dioxide would give me 2 oxygen atoms times, of course, the number of moles, which is in this case from carbon dioxide, which is 4.6 divided by 44. Remember, I did not handle that 10 to the power 23. All I wanted to do is do the algebra without the power. So it's going to be 3.76, if you care, times 10 to the power 23. But I don't know how GeoGebra really does it in here. See how it does, puts a bunch of zeros in there. I don't care about those zeros. All I want right now from GeoGebra is to give me a calculator, basically. From your calculator, you give me just these numbers without the power. So it's 3.76. So let me go back into my screen where I was doing the calculations, which is here, OneNote. And basically the answer, therefore, is 3.76 times 10 to the power 23. Remember, the moles are in grams. So we want it in kilograms. So we're going to divide by 1,000 again to convert it back to kilograms. So 3 is deducted from that. So the answer basically is 3.76 times 10 to the power 20 kilograms. That's how much water we're going to end up with. And it tells you in the problem to compare that number to what Earth has. So this is Venus. So what Earth has is 1.4 times 10 to the power 21 kilograms of water in its oceans. So if I do the ratio of the two, namely 1.4 times 10 to the power 21 divided by 3.76 times 10 to the power 20, obviously 20 when I deducted from 21 is 10, and I will be left with 14 over 3.76. So again, I'm going to go back into my calculator in here and punch in. So I really don't need to share it. All I'm doing is just dividing 14 by that number. So any small calculator can do this one in here. So again, this number, 14, that's the Earth divided by 3.76. It gives me about 3.7 times. Okay, so it's about 3.72 more. So the Earth has almost 4 times more water than if you take all of the water on this, all the carbon dioxide on Venus and convert it into water. Even if you do that, you still have more water on the Earth than Venus does. That's problem one. Problem two in here, if you were to take all of that water basically and stack it on the surface of Venus, how big the... Now I need some numbers. If I go back into the book, that's why I have to really look for the book. And I'm looking at the appendix on A3, appendix A3, which is on table 5, okay? Table 5 on the book. Table 5 on the book gives me the radius of Venus. So it gives me the radius of Venus. R of Venus equals to 6,052 kilometers. I need it in meters, so I need to multiply it by 1,000. So I need it in meters. Or if I took the decimal points, those are 3 plus 3, that's 6. So it's 6.052 times 10 to the power 6 meters. So that's the radius of Venus. The reason why I need the radius of the Venus is because I need the surface area of Venus. The surface area of Venus is like in a sphere, 4 pi times the radius squared. So if you don't remember this formula from your geometry class from high school, that's how the surface is. My screen is not acting right now. You put this away because what I needed from it right now is just I probably need this appendix, so I don't really know what this page does. Anyway, so again, the surface is equal to 4 pi times r squared. If I multiply it by the height, my camera is kind of if I multiply it by height, I'll find the volume. So the volume is equal to 4 pi times r squared times the height. This is the volume. But I know how much water we're getting in here. We know how much water. It's actually this much water from the previous problem. This is the amount of water that we're going to end up with on Venus. Now, each 1,000 kilograms of that, according to the problem, is 1 cubic meter. That's the density of water. So that means I have to divide this by 1,000 to find the actual volume of water. So the actual volume of the water is going to be 3.76 times 10 to the power 20 divided by 1,000. So this volume must be also 3.76 times 10 to the power 20 kilograms. But if I have to divide it by 1,000, now I'm going to get it in cubic meters. Because each kilogram weighs this much cubic meters. I don't need to write this one. So the kilogram cancels the kilogram and the cubic meter goes upstairs. So the point being in here is I have how much volume of water is. This number, I know what it is. It's actually 4 times pi times r squared. Then r is the radius of Venus, which is 6.052 times 10 to the power 26. I have to square that number. And then I get the height of the water, Of course, 1,000 in here, 3 zeros cancels with 20, so I have 17 in here because I have to deduct it from 3 deducted from 20, that's 17. So the answer in here for the height is 3.76 times 10 to the power 17 divided by 4 pi times 6.052 times 10 to the power 6 squared. I'm going to punch this in a calculator because I can't do it with fast enough. So I'm going to stop the sharing in here, and I'm going to pull that calculator again. Share. Where is my calculator? There it is. Okay, so what I have in here, let me push this screen up there. Okay, so I probably lost it in here, so I may have to stop sharing again and share it because again, it's kind of hard when I'm doing it by myself here. So again, so let me go in here, share again, this calculator. Okay, because I need to see what I'm going to punch in here. So we have 3.76 times 10 to the power 17, divide that by 4 times pi. GeoGebra program I'm using calls the pi, which is easy. Open parenthesis, 6.052 times 10 to the power 6. And the whole thing is squared, remember? That's the radius squared. And it gave me 816.92 meters. 817 meters, basically. That's how high it is, less than a kilometer. Okay, so I'm going to go back in here, stop sharing. Obviously, you have to do the calculation to convince yourself everything is working in here. So I'm going to share again this thing in here. So the correct answer now is 817 meters. That's how high. It's less than a kilometer. Remember, some oceans here on Earth, they are as deep as about 10 kilometers or 11 kilometers in the Pacific Ocean. So this is not that, it's kind of shallow, relatively speaking, compared to what we have here on Earth. So that's basically the answer to that question. Let me minimize the screen in here. So we did this too. The third one, it says in here, Kepler's law. So let's do that quickly. Let me try to understand. Probably it's a good idea to... Should I draw these things? Let me go ahead to get into GeoGebra and draw these things quickly here. So again, I'm going to come back in here, stop sharing. I'm going to share back. So if you don't have GeoGebra, if you don't know how to use it, don't worry about it. I mean, you can do it by hand, so it's not really that... all you need is a calculator and everything else is fine. So I'm going to draw a circle in here, centered around 0, 0. And circle. No, let me do it graphically. Why am I going to do it manually? I mean, programmatically. What is this circle in here? Is this a circle? Yeah, here is the circle. So this is basically, I don't know if you guys are looking at GeoGebra or not. So this is basically the path of one of the planets. Let's say, for example, this is Venus. I'm going to draw then a bigger circle, which is centered around the same thing in here, which is the Earth. Okay. And here, I'm going to draw a small circle now, still. So this would be the planet Venus, okay? And this would be the planet Earth. And this, of course, is the sun, okay? So all of this is the sun. You can fill them. You can do all kinds of things if you know how to do GeoGebra. I mean, what you got to do is just go to the properties and pick up an object in here. Oops, I don't know what this is. So this is the sun. So you can go to the settings of the sun and change the color if you care to. You want to make it red, go ahead and make it red. And actually you can fill it. Where is the fill? And you can make whatever color you can make. Okay, so the sun is probably yellow and so on and so forth. Okay, I don't know if you can see it in here. Maybe it's not that yellow. Anyway, so the point being in here, you can have fun with this one if you want to, but that's not the point. Okay, that's not the point. The point is the following. You are on Earth. You send a beam of light, it goes, hits the sun, comes back, 276 seconds. So the time, I'm going to call it time. Time is 276 seconds, okay? That's the time it takes for the signal to go back and forth. The distance from the Earth to the sun is 1 astronomical units. They tell us the distance between the sun and Venus is 0.723. So the distance between the Earth and the sun is going to be equal to 1 astronomical unit minus 0.723. Okay? Which is, why is it giving me this thing in here? Let me go to settings in here and let me change it to, it's giving me 2 decimal points. That's why you're seeing that. So let me pick up 5, okay? So that's better, okay? So it's giving me a 2 decimal. In your calculator, you can pick whatever decimal points you have. At the end, we need the correct answer though. So this is the distance in astronomical units, not in kilometers. But we know the speed of light, let me call it speed, is equal. Again, I'm looking at this table in here, which is the table in front of that table that I looked on, which is table 1. As a matter of fact, this table was given to you as part of homework 1. So the speed of light is equal to 2.99792. You can write 300,000, but that's going to give you an approximate value. So we want really more of a precise value. Times 10 to the power 8. Okay, I'm going to not write the power right now. Okay, I'm not going to write the power right now because okay, I don't like the slider. It's not the slider. Again. And you see in here the precision, again, the same thing that happened earlier. So there's just a setting in here, that's all. So let me go. So on your calculator, you're going to pick whatever numbers you have in here and there, okay? So I'm going to pick right now, what, 10 sig figs. No, 10 decimal points. Okay, so that's better, okay? So everything now is went crazy in terms of numbers. Still 7.92458. Okay, so that's the speed of light. It went back and forth. That means the time it takes for it is half that time to go from the Earth to the Venus. If it bounces back, so it's going to take half that much time. And we know the distance. So all I have to do now is divide. I wrote it wrong. So this should be speed. Okay. So we have the speed, we have the time, and we have the distance. So now we can calculate the distance in kilometers. Remember, I have to multiply it by 100 million, 10 to the power 8. I'm not multiplying it right now, okay? I'm going to leave everything in terms of 100 million. So speed times time, which is half that much. That's going to give me the actual distance in kilometer. Actual in kilometers is going to be equal to actual distance between the Earth and Venus, okay? So this is actual Earth, Venus, okay? So this distance is equal to speed times the time. Remember, the time is half that much because that time is goes back and forth, okay? So we want to just half that much to go only once. So this is 413 million kilometers. But that represents only this fraction of an astronomical unit, okay? The distance between the Earth and the Sun. So the distance Earth-Sun, which is the astronomical units, okay? That is what an AU is. If you want to, 1 AU should be equal to that number that we found at the actual distance between the Earth and Venus divided by this fraction of an astronomical unit, which is called distance in here. Okay? Where did I get an U in here from? I don't know what this number is coming from. Let me delete this thing. I don't know what happened in here. Okay, again. So the distance in AU, oh, that's what it's called astronomical units. What is this in here? I'm sorry about this thing in here. Okay, so again, let me go back. I'm having issues with the computer right now. Let me delete this, okay? And delete this. So again, astro unit, that should be equal to this distance divided by this fraction of a distance. That's going to convert back into an astronomical unit. So it's an actual Earth-Venus divided by the Earth-Venus in terms of astronomical units. Okay, finally I got the number. Sorry, it's 1,493, basically 100 millions of meters. We want to convert this back into kilometers by dividing this number by 1,000, because the standard value is written really in thousands. So I'm going to divide this fraction by 1,000 to convert it back into kilometers. And the answer is 1.49355 times 10 to the power 8 kilometers, or 149.3 million kilometers. Remember, I did not write in here somewhere the speed of light. There is a 10 to the power 8 in it. So if I fix that and put a 10 to the power 8, so everything will be now in terms of kilometers. So it's 149,355,087 kilometers. That's what an astronomical unit is, okay? So that's basically for this problem. So again, here's the trick. You find the distance between the Earth and Venus. And that distance is 0.277 astronomical units. So you're going to find it in kilometers and astronomical units. So all you have to do is divide that distance by how much it is in astronomical units. That gives you how many astronomical units are, how many kilometers are in an astronomical unit. So let me go back into the schematic to explain this plan. It sounds far more complicated than what honestly it is. So let me go back into here. Okay, so again, let me share my screen in here notes. So here is the plan. So here is Venus, here is Earth. That's where the sun is. We don't care for it. This distance, when we did the calculation, is 0.277 astronomical units. All we have to do is deduct 1 astronomical unit for the Earth, minus in here that's given to us 0.273 astronomical units. Give us this difference. That's what we did. Then we sent, a laser beam back and forth. That took 276 seconds. Only one-way trip is 138 seconds. Okay? That's how much it takes for light to go from the Earth to the sun. From light to Earth, from the Earth to Venus. If it bounces back another 138, that's the round trip. We want just one way. So 138 seconds, we know how fast light is. It's approximately, it's 200, and we have to really use the correct value. So we can't use 300,000 kilometers per second. We have to use the more accurate value, which is 299,792.458 kilometers per second. That's gonna give me a more precise answer. Okay, so we multiply 138 times this number. That gives us the same distance in kilometers. So we know this distance in kilometers, and we know it in astronomical units. So all you have to do is take the ratio of the two, this distance that we calculate in kilometers, which turned out to be 400 and, I'm trying to read it in here. It's a big number in here. I have one decimal, 3, and 3, and 3, 41 million something kilometers, okay? When I do that, I have to divide it by this number to find how many actual astronomical unit is. And that gave me 149,355,087 kilometers. Usually people write it as 1.5 or 150 million kilometers. That's basically what people say. Obviously, the correct answer is 149,000,355. That's more accurate answer for this distance. Okay, I think I probably went too far in this problem, more than I should, honestly, but it's a lot simpler than what probably I'm trying to explain it. So if you guys are confused about it, please let me know. And it's a lot simpler than that, okay? So if you have any questions about it, please don't hesitate. And sometimes when somebody over-explains something, it becomes a little harder than what it should be. And sorry about that, okay? So again, that's the math behind it. All you have to do is subtract these two numbers and then find the time, which is half the time, and then multiply it by the speed of light, and then divide by the ratio to convert back into what an astronomical unit is in terms of kilometers. Okay, next problem. Where did it go? Okay, so the next problem has to do with the Venus and Earth. They're in inferior conjunction, and you can read about it in unit 11. That's when it talks about the planets in general. But for the case of Venus, it takes 583.9 days to align itself back with the Earth, okay? So we can argue. So if you look again at the book in here, and it tells you how long for Venus to go once around it, and it's actually in unit 39, okay? Unit 39 from the book, it tells you that it goes once around, it spins basically backward around its axis, and it takes 117 days, okay? It takes 117 days to spin. So basically at that point, all you have to do is, let's go back into the diagram in here that I start drawing with the GeoGebra, because that's going to be helpful to explain a little bit what's going on. So I'm going to stop sharing. Let me share now this diagram. Anyway, so imagine the following. So I'm looking at this graph. Imagine the following. After the Earth, 583.9 by so the way divided by 583.9 minus 365. That's how many 0.25 to be more accurate, okay? That's the Earth year. So this how many days? 583.9 days. For the next alignment, the Earth would have spun one full year plus 218 days, 219 days. 219 divided by 30, that's going to be 7 months. So the Earth would have gone basically, okay, what is the, can I move this point set? No, I can't. What is the C in here? Can't move. Anyway, so I'm going to draw a new circle, okay? So the Earth would have gone 6 months plus something, 7 months, basically. So the Earth will be in this position here. So why is it not giving me? Let's make it into 1, 2. Okay, that's too big. Let's make it 1. Okay, and even that's too big. Okay, let's make it 0.5. Okay, so that's the Earth. Okay. So that's after 1 year, basically. 1 year it goes back, and then 7 months. 6 months is here, 7 months is there. Venus would have gone how many? Remember, it rotates 117 days, so 583.9 divided by 117, that gives me 4.999. So basically it went 5 times. Okay? But then it would have aligned itself back with the Earth. So again, I'm going to draw a circle in here. For some reason, it's not. Can I do this? Yeah. So this would be Venus. Okay? And it has spun exactly the same amount in here. So whatever was facing away from the sun is facing away from the Earth. So they're going to be in phase. They're going to be in sync. They're going to be let me read the problem again to give you the correct wording of the problem here. Okay. So Venus, so show that they're nearly the same side. So it's almost the same side, not quite exact, because of the fact that this is not exactly 5, but rather 4.99. So almost the same face, always be facing the Earth when they align up again next time around. Okay, so that's this problem. The last problem in here, it tells you that if the Earth were to go around the sun, but instead of the sun rising in the east and setting in the west, it would rise in the west, setting in the east, meaning it's spinning backward, retrograde. So in that case, remember, I probably could use the same diagram in here is fine, or maybe a different one. That's fine. We can use the same diagram. So let me change this thing in here. Let me explain it basically. The sidereal day for the Earth, so ignore Venus for right now. The Earth spins in its axis, makes a rotation every 23.56, 23 hours and 56 minutes, basically. Meaning it was facing the sun today at noon, versus the background stars, it's facing north, for example, facing up. After 23.56 hours, it's going to be facing up. You need to wait that extra 4 minutes for the Earth to line itself and face the sun. That's why the solar day is a little longer than the sidereal day, the day with respect to the stars, by about 4 minutes, because the Earth has to make that extra turn to align itself with the Earth, because it's moving forward and spinning at the same time. So as it spins, it will make a full rotation facing the stars. That is the sidereal day. Then you will need to wait a few more minutes for it to line itself back to the noon, so that the noon is in noon. Okay, so that's the sidereal day and the lunar day. Now imagine if the Earth is actually spinning backward. So the Earth would align itself with the stars, would align itself first with the sun before it aligns itself with the star. So in that case, the sidereal day will be longer than the solar day. Okay, you can do it by construction, but actually it should be intuitive enough so that you can see it. Okay, so it lines itself with the stars, but the sun is there, so it needs to wait extra to align itself with the sun. So the solar day now is longer than the sidereal day. But if it were to spin backward, it's going to line itself first with the sun and then with the stars. So in that case, the sidereal day will be longer than the solar day. Okay, I think I spent far more than what I really wanted to on this discussion, but hopefully it's clear enough. If it's not, please shoot any questions and think about them first. You should be able to understand them. And if you still have difficulty, please let me know. Again, make sure you read the units. Make sure you're going through all of your assignments properly. And I hope that you will not have any difficulty with it. Thank you.